I would like to thank the organizers very much for inviting me. And to begin with, I want to put things into a classical perspective. So throughout this talk, we will be looking at holomorphic, proper, smooth mappings of complex manifolds. So for the purpose of this talk and for various other reasons, we can assume that the base is always smooth. In some of the cases I'm going to consider, this will be automatic, in others not. And next rule would be all coherent sheaves are locally free by assumption. And so here are the Hodge bundles, and we can see that these possess intrinsic inner product given by the wedge product of P of forms, provided there is maybe a Kähler metric present, which in the classical case here will be not really necessary, but later it will be. So I will focus, say, on the Hodge bundle F lower star of omega n of canonical forms, or F lower star of kx over s. And so the Hodge metric is given as L2 inner product of canonical forms. And so in Griffiths computation of the curvature, the Kodaira-Spencer classes play an important role. So we look at sheaves of holomorphic vector fields. So first the ones which are tangent to the fibers. This is Tx over S. These are sitting in the space of, in the sheaf of all holomorphic vector fields, and the co-kernel is generated by holomorphic vector fields which come from the base. And we can say if this sequence possesses a holomorphic splitting, more or less, it means that we can lift holomorphic tangent vectors to tangent holomorphic vector fields. And this means that the family is, say, at least locally holomorphically trivial. So the obstructions against such a family being holomorphically trivial are sitting in the first cohomology, and we are looking at the edge homomorphism, which in fact is the given by the Kodaira-Spencer map. And so we are looking at 0, 1 forms with values in the sheaf of holomorphic tangent bundles, and everything is restricted to a fiber. So the curly X is always the total space of a family, whereas the capital X stands for the fiber. All right. Now one can easily see that there is a cup product of such forms, a contraction with canonical forms, and so we get from the Kodaira-Spencer class and the canonical form a n-1 0 form. And so in Griffith notation, one would put the tangent sheaf of the space at the bottom to the right-hand side, and the curvature was computed. In his notation, the curvature form applied to a section paired with another section is given in this way. And so everything is induced by a flat metric on a certain sheaf, but I don't want to speak on about Hodge theory. Now, the other way of saying this is we look at the curvature tensor, so we plug in the two tangent vectors of S and two elements of the fiber, and then this is the canonical given by this inner product. And so our aim would be to construct an intrinsic metric on the base of holomorphic families in general, which is functorial, so meaning it ought to be compatible with base change. And the reason for this is if it is intrinsic, then it will descend to the moduli space. And that is the aim of the approach. So for us, mostly, a Calabi-Yau manifold will be a Kähler manifold whose first real Chern class vanishes. And of course, this would also include whatever elliptic curves and K3 surfaces. And most of what I'm going to say would also apply to these. And now, according to Yau's theorem, there are various Kähler-flat, Ricci-flat Kähler metrics. So given such a Kähler form, omega x, we take the nth power where n is the dimension, and then we have a Ricci-flat volume form. So 0 is the Ricci form of volume form equals minus I dd bar log of the volume form. And so the notion of a polarization comes up in algebraic geometry. One can say that it would be the class of an ample line bundle, and for us it's a Kähler class. And so a polarization would be a 1-1 form, 1-1 class, sorry, which is real and represented by a Kähler form. And then we need the notion of a polarized family. And for me, it would be a section of R1 F lower star of omega 1 x over S. And this approach has the advantage that taking base changes and so forth, that this is kind of compatible with the complex analytic methods. And the restrictions to the fibers are by assumption polarizations for the fibers. Now, there is also another approach, and yeah. And one could also say we have a family x over S, and then we write down something like lambda tilde, and lambda tilde would be just a section of this bundle such that lambda tilde restricted to a fiber is a Kähler class. And then in a manuscript of Fujiki and myself, the first point was to see that these two definitions are actually equivalent. All right. Now, Yau's theorem states the existence of a unique, well, yeah, it's very unique, Ricci-flat form in any Kähler class lambda of x. And so then we are looking at a polarized holomorphic family of Calabi-Yau manifolds. Now, so we need some holomorphic dependence of the Kähler classes, and one can see here, like, on one hand, a polarization for a family is a real object, and on the other hand, we have something like some holomorphic section of something, of a coherent sheaf. So this means, like, it suggests that this is constant in some sense because it's holomorphic and real, say. Okay, now we then can see that we have Kodaira-Spencer classes, and the Weil-Petersson metric on the base of a holomorphic family is given exactly like in the classical case. Namely, one takes the inner L2 inner product of harmonic representatives, and this is exactly what André Weil suggested. At the time, there was Teichmüller theory, and André Weil suggested that one should use modern deformation theory, and this led him to this definition, and the A's in dimension 1 are the harmonic Beltrami differentials, which are explicitly known. Okay, so we know also that this Hermitian inner product on the base gives us a Kähler structure, provided the holomorphic family is effective. If the family is trivial, of course, then we only have here zeros, and so we cannot expect a Kähler form by such a construction on the base. So in the case of families of Calabi-Yau manifolds, one is able to identify the Weil-Petersson inner product. And so at this point, we assume that the canonical bundles of the fibers are actually trivial. And we take a section. And then for holomorphic symplectic manifolds in the sense of hyper-Kähler manifolds, one can do this construction. And what you see here is this one here more or less is the definition. Because here is a volume form, and this is the pointwise inner product of the harmonic Kodaira-Spencer forms. And then one would look at the whole construction closely, and then one can show this equality here. And now this formula here looks very familiar. So this is just like the invariant form on a symmetric domain. And then Tian noticed that the same proof also works for the case of Calabi-Yau manifolds in general. And so the next point here is that, well, we have a consequence. So if we look at this thing here, so let us see. If we take the derivative of the logarithm here, and if we notice and consider that we have holomorphic objects there, and we have, say, harmonic Kodaira-Spencer forms in order to do the calculation, and then it is clear that one ends up with this formula here. Now, it's hard to pinpoint where this comes from, but one can find this in a paper by Chin-Lung Wang. But he does other things in his manuscript. All right. So what we have gotten here is a potential, a DD bar potential for the Weil-Petersson form, and then we can see that this is just the curvature form of the Hodge metric on F lower star of K x over S. Now we turn to the relative canonical bundle itself rather than its direct image, and we assume this very general definition of Calabi-Yau manifolds. And so we want to compute the curvature, and which is very close to what we have seen before. And so we need some notation. Once again, the relative Kähler form, so the form of all of these Ricci-flat forms on the fibers, we saw that these depend in a differentiable way of parameters. So we have a relative Kähler form. We got a relative volume form, which is this one. And the next step is we are looking at the curvature form of this. Well, maybe there is an extra sign. No, well, the sign is gone by the C. All right. So this is the curvature form of the relative canonical bundle. And while we already know on the fibers we have the Ricci forms, which are 0. And also we know that the push forward is the Weil-Petersson 4. And so then there is a fact to mention that if we are looking at the induced Hermitian metric on the relative canonical bundle, then we get this formula. All what is left is 1 over the volume of the fibers, which is constant, times the pullback of the Weil-Petersson form in the general concept. And yeah. So our question will be, can the relative Kahler-Einstein be represented first by a real 1-1 form on the total space, and maybe is it induced by a Kähler form on the total space? And that is what I would like to talk about. So part of this thing is already answered since quite a while. Namely, locally with respect to the base, one can always produce such a thing. And so one can even make this form Kähler by adding a pullback of a Kähler form on the base, where the base is a local object at this point. So if the polarization can be represented by a closed real 1-1 form or beta Kähler form, then this form on the total space can be chosen globally as a 1-1 form. And so the usual approach, of course, is first the following. We start with a, call it tau u over u. So then we have a Kähler form at the top. Kähler, or yeah, at least strictly positive on the fibers. Then we are looking at tau u restricted to xs. And then the continuity method gives us a function so that I dv bar of, say, phi u, such that this thing, well, first of all, it's sitting on the fibers, living on the fiber, so that this is Kahler-Einstein. Okay. And then the next step would be use the implicit function theorem to see that we have here tau u restricted to s. This is known, but we see that these phi here depend in a C infinity way upon the parameter. So we can write down something like this thing and call this, say, for the moment, omega u. Then we see that omega u restricted to the fiber is omega xs, the Kahler-Einstein on the fiber xs. So this is what happens. And then, of course, we could also say the following. this thing, this function here is not quite uniquely determined, but what one can do is one can normalize omega u to the power n plus 1 that this is equal to 0. So here we have something like a fiber integral. So what we are doing here is this thing is an n plus 1 comma n plus 1 form, and we integrate it over a 2n dimensional, real dimensional fiber, and then we are left with a 2 form. Actually, we are left with an with a 1-1 form. So this here is a 1-1 form. So this, okay, and it's fairly easy to do this because, well, then one matter of notation. If I say whatever omega u to the n, this is supposedly by definition 1 over n factorial omega u wedge omega u n times. And the advantage of such an approach is that the binomial coefficients all become 1. Right. So this means yeah, alpha plus beta to the power n equals the sum alpha j wedge beta n minus j, which simplifies our notation. So we don't want to carry around all of these numerical factors. All right. So in this sense here, we would say if this is not the case, so we get something like a form omega s. And the next step would be just to look at omega u minus omega f upper star of omega s. Maybe we need a constant here for some volume, and take this thing, and this does what it is supposed to do. So it's a little argument, but very transparent. Okay, and but this situation tells us that the polarization under such an assumption is the following, namely, we could say in this case, the class of this one here, this will be some, say, lambda x in H2 of XR. And of course, this gives us some element in R1 or R2 f lower star of R of S. So this is not an arbitrary polarization, but one that is flat. And one could also suggest, but I'm not able to see directly, so this still has to be decided, whether as an assumption also it would be sufficient to say that we start from some element lambda in here. But the type consideration is a problem because at this point x would not be, for obvious reasons. All right. Now, so now the real question is there a Kähler form on X whose restrictions to all fibers is Ricci-flat? And please note that we are not dealing with a compact manifolds X and S, and so one would assume that this is maybe part of a degenerating parameter. Okay, so as I said, locally this is clear, but globally it is not. Now here's the answer, joined with Matthias Braun from Marburg and myself. And so we start with a polarized family. So assuming here that the polarization is induced by the Kähler class. Now we assume that the Green's functions for the Laplacian of functions on the fibers are uniformly bounded from below. Bound has to be a negative constant, obviously. And under this condition, there exists a Kähler form on the total space whose restriction to the fibers is the Ricci-flat form on the polarized fibers. And so the question is how to verify this kind of unpleasant assumption. And certainly in the compact case, it's clear. So classical theorems tells us that the Green's function is bounded by a constant depending on the diameter of the fibers. And we can see that this, this assumption is not contained if we are looking at whatever varieties of general type or whatever hyperbolic Riemann surfaces. Then in a degeneration, the Green's functions are certainly not bounded. But people have been working on this question, and here is an example, an answer in the projective case for projective families of Calabi-Yau manifolds, meaning allowing for some degeneration. Takayama and Zhang found out that, that the diameter is actually bounded. And then there is a recent result by Zhang and Tosatti who show that for polarized families of Calabi-Yau manifolds, under mild assumptions for the type of degeneration, we have this thing. So the boundedness of the diameter. The assumptions on the type of degenerations are weak, but a bit technical. Okay, so this answers the question. And now let me come to a related corresponding situation for twisted Hodge bundles in the canonically polarized case. So there is one remark, but maybe before I come to the twisted Hodge bundles, I may make some remark on the canonically polarized case. So assumption is the canonical bundle of our manifold is ample. And here are the notations. So we start with from a Kähler form, then we got a volume form. The Ricci form of the volume form is minus I d bar log of the volume form, and then the volume form inverse gives us a metric on the canonical bundle. And the theorem of Aubin and Yau says the existence of a unique Kahler-Einstein metric. So the Ricci tensor is up to a sign equal to the metric tensor. And this is the case we are going to look at. And so when, all right. Yeah. Then there is another ingredient of what I'm going to say. So the other ingredient is the notion of a horizontal lift of tangent vectors. So we are looking at a tangent vector of base. We have some form on X, which is real, declosed 1-1 form with the property that on the fibers it is positive definite. And then this is sufficient to say we take a lift of a tangent vector and which is perpendicular to the fibers. If we say so, then we write down the lift, and the lift ought to be of also type 1, 0, so there is no dc bar involved. That is not necessary. So a complex lift, if you want to say so. And then the coefficients can be easily determined from the components of the metric tensor of omega on omega x. And so here are the conditions. We start from a tangent vector, then we take a lift, so it projects down to the given one, and it is perpendicular to the fibers. And then there is the notion of a geodesic curvature. So I had been looking at this quantity, but I found out that it carries the name, or was given afterwards. I don't know. At least it carries the name of a geodesic curvature. So one can do such a construction whenever we have such a form on the total space. So this is the inner product of horizontal lifts. And we could see that the Kodaira-Spencer map is given by the edge homomorphism of the short exact sequence we had been looking at. And of course, in Dolbeau cohomology, the edge homomorphism is given like this. We lift the tangent vector in a differentiable way, for instance, in a way that the lift is perpendicular to the fibers. Then we apply d bar and restrict it to xs. So then this formula immediately tells us that the thing is d bar closed, but not d bar exact, because we need the horizontal components in order to write down d bar. Okay. Now, here is a theorem we would need, namely the positivity of the relative canonical bundle. And the way how to see this is very short. And so it fits on here. So what we do is the following. We start from omega x over s. So this is the relative Kahler-Einstein form. So omega x over s on the fibers is the given Kahler-Einstein metric. And by the implicit function theorem, these depend in a C-infinity way on the parameter part. So then we take omega x over s to the power n. And so then this is a relative volume form. If we wish, it is G dV. So G minus 1 gives us a metric on the relative canonical bundle. And so we say omega x equals I dB bar log omega x over s to the power n. So that is the curvature of this thing, and this is now living on the total space. Fine. What we do is we restrict omega x to the fiber, and what we then get is the definition of minus the Ricci tensor, or Ricci form, So then this is omega xs. Now comes the following formula. Omega x to the power n plus 1. This is equal to something like Vi inner product Vj. So this is the geodesic distance times omega x to the power n. So here is the volume form. So we could also say GdV wedge, and then we take here the sum of dSi wedge dsj bar, or we could also restrict it to a one parameter family. That would be good enough. So let's call this Vij for the moment. So, this thing is a certain determinant. And what we know, we say we are on a one-dimensional family, then the omega has already n positive eigenvalues, and we just need one direction more. So this is the reason why we are doing this. And then comes the crucial formula, which says the Laplacian on fibers plus identity of phi j bar is the pointwise inner product of the Weil-Petersson form. Now, if we integrate the whole stuff, then we get the inner product, the component, so to speak, of the Weil-Petersson form. But what we can see here, the right-hand side is positive definite, in the sense either we do it on one dimension, then it is a positivity of numbers, or in terms of matrices, it is, this matrix here is obviously a positive definite, and then we have this operator here. Now, this means we can apply the inverse, and this means that this thing is positive. Now, we can say even more, and before what is the essence of this equation? So when dealing with such things, computing curvature and so forth, the critical thing are horizontal derivatives. And we want to replace horizontal derivatives by intrinsically giving tensors. So a horizontal derivative of any kind in the I direction should be replaced by the Kodaira-Spencer form in this direction. Then we have a result, otherwise not. And so what this device here does on the left-hand side, this thing eliminates from this geodesic curvature, it eliminates the horizontal directions. That is what it does. So we see that this box is minus the operator given by second order derivatives. So this is by definition the positive Laplace. And all right, and from this formula here, we can also do the following, namely, we can say that Vij is larger than a certain coefficients depending on the dimension and diameter of the fibers times omega WP and the IJ's component. So what we can say here is that this part can be estimated, but once again, also here the diameter of the fibers is essential, and this comes from computing the resolvent kernel. All right. So this is what we have gotten here. All right, so here are these equations. And if the intrinsic version of what I wrote down here, this one, and here is the curvature formula for this thing, for the twisted Hodge bundle. So while we don't want to look too closely at this formula, there is one thing. Question is positivity. One knows, or well, one has to compute the spectrum of the Laplacian here, and there are no eigenvalues in between 0 and m other than 0, meaning that the only negative contribution to the whole thing is this one. If we apply the formula to p equals n, then the third term is not there at all. In dimension 1, the third term also does not exist, and then also the second and the first term are the same. Okay, anyway, so there is a formula, and so it already existed. First thing is by duality for m equal to 1 and changing the sign of the formula, we arrive at the result for these bundles here. And for those, previous results exist. So Scott Wolpert gave the result for a dimension for 1 and p equal to 1. And there is also a formula by Fischer and Tromba, which is closely related somehow. And then for p equals 1, Zio gave a technical result for the curvature. And so there are applications. One application of the curvature formula is that the moduli stack of canonically polarized manifolds is the Kobayashi hyperbolic with emphasis on stack, of course. And then another corollary of the formula is the effect that the direct image is Nakano positive. And of course, all we need for Nakano positivity is that these coefficients, I should mention that this is positive, otherwise it would be meaningless, of course. All right, and then one could also look at a theorem by Berndson, who looked at such direct images. Now, if I plug in the fact that the relative canonical bundle is positive, then I can use it at this point, and I get Nakano positivity once again. There is one thing I would like to mention about dealing with these sheaves. Namely, all of these computations, so we are looking at sections, or we're looking at the sheaves with the assumption we restrict ourselves to a locus where these are locally free. And if we want to compute curvature, the only way is to use differential forms, obviously. And so what can we do? So we can replace these things, represent by forms, say psi, which are d bar closed forms on the total space with values in the corresponding sheaf. So one might expect that one could work with p comma n minus p forms on the total space, but this is utter nonsense. This immediately yields a contradiction. So this is what one can do. And for instance, so if we are looking at our QF lower star of E, say a Hermitian vector bundle, then say of S, so then we can see what happens. Sorry. Let us stick to this this situation. S times R P F lower star of n minus P x over S. And so in this case, this also applies to the twisted situation, otherwise nothing new would be done. N minus 1. And then this is then, we have here psi, and here we have chi. And then this goes to F lower star of, well, something, and in the end we got OS of S. And this thing is just given by the fiber integral, psi wedge chi. So as an exercise, we can see their duality for such sheaves. And what we know is that this thing here, d bar of this one, is the integral of d bar of psi wedge chi. And this is 0. So we really get from d bar closed forms here, we really get a holomorphic form. So this tells us that this is the correct approach. Use d bar closed forms with values in omega x over S and say twisted by L, where L could be the canonical bundle or anything. So this is some remark about this, and the rest of course, is very technical. Okay, then there exist results by Murugan and others. Murugan, Takayama, Murugan, Takayama, and Liu Yang. And so here is something about the twisted Hodge bundles general case. So let us forget about the canonical polarization, and we assume that there exists a relatively positive line bundle on X, or strictly positive on X. And then one can do the same kind of thing, say omega X is defined to be the curvature form. And then one has induced Kodaira-Spencer forms. And here we are given one family. This is not about moduli spaces, but about given families, obviously. And then we can write down the geodesic curvatures. And then there is the following theorem by Philip Naumann from Marburg. And he has the following result. We start from a positive Hermitian line bundle, and then he can prove the curvature of the twisted Hodge bundles. And what we see is here is the geodesic curvature, and the rest looks similar. Once again, P equal to N yields the curvature of the direct image. The third term is not present. And then, what else can I say? The function phi is actually positive, or say positive definite if we look at the whole matrix, is positive if the line bundle is not relatively positive, but as it is stated here, positive on the total space. Now, this thing contains both known results, the one of Berndson and the other one I had been talking about. And yes, so he is going to extremes and using Lie derivatives for differential forms with values in Hermitian line bundles. So, but the thing works. Okay, so I would like to make some remarks about methods. So we have been talking about Calabi-Yau with the Calabi-Yau theorem, and one of his Calabi's, the first theorem on this was the case that holomorphic forms, holomorphic vector fields, or holomorphic tensors are always parallel with respect to a Ricci-flat metric. And well, the notation we have been using this implicitly, and here is once again the picture of a harmonic, of a horizontal lift, and also in the Calabi-Yau case, the horizontal lift yields harmonic Kodaira-Spencer forms, but this is takes a little more effort because if B1 is positive, then we need to be, it's not so easy what we are doing. If B1 is not zero. So, okay. So let me look at the curvature form. So we are in the general case. Theta is the curvature form of the induced metric on the relative canonical bundle, and please disregard this minus sign. There was previously none, and here there should be any, because it's the curvature of G to the minus 1. All right, so we already know that there is no component here, and the question is about this one and these two. It turns out that the mixed components which show up are, to begin with, give holomorphic one forms, and this is this computation. And so then we have this kind of lemma, and it says if the harmonic, if the Kodaira-Spencer tensors which we constructed are harmonic, then these components are also zero, the holomorphic one forms or the 0, 1 forms which occur are equal to 0. And so we need a couple of quantities. The first thing is we write down the inner product of horizontal lifts in terms of the curvature of the relative canonical bundle. So one can do this. So this is by no means definite at this point. So this is the formula for the lift. If we write it down, then this comes out. And then we have such a formula. And this formula tells us that the Laplacian of a certain function is non-negative. So if we do this for a general base, this equation has to be read as a matrix of Hermitian functions, and it says positive semi-definite. All right. So, but what it tells us, of course, is that in the first place, the Laplacian has to be 0, and in the second place, these are equal to 0, all of these components. Okay, so this is what we get. And yeah, so I don't know, given the time, I don't know whether I want to give the calculations for that, the arguments. This is like using the Ricci-flatness of the metric tensor extensively and the standard equalities of differential geometry. And then the next fact is this one, the Laplacian of the components here, the horizontal components of the curvature of the relative canonical bundle is equal to the Laplacian of chi. So this immediately follows from this equation here. And these are equal, and this equation tells us that the Laplacian of chi has to be 0. So these components there are 0, Laplacians are equal, and the Laplacian of the former term here is 0. Fine. What does it mean? These are fiber-wise Laplacians, so it means that all of these components only depend on the parameter. And so then, of course, we can compute the value by integration in the following way. We take the geodesic distance functions here, and we arrive at such an equation. The Laplacian of phi is equal to this thing here. Once again, this is some computation. And of course, from here, we know this fact, but we are now looking at the following thing. On the other hand, we know from the normalization that omega x to the n plus first power, this fiber integral was normalized 0. And so that means the fiber-wise harmonic projections of the phi ij, they need to vanish, because this is here what we get. We take the integral is 0, so the harmonic projection vanishes. And then we can say that phi ij, this is the coefficient of omega x to the n plus first power, is equal to the Green's function of the Laplacian. Then we should take into account that this depends only on S. So in terms fiber-wise, this is a constant which can be disregarded, and we are here. By assumption, the Green's function satisfies such a condition, and it's bounded from below. So then we can say that the Green's function of the pointwise inner product of the harmonic Kodaira-Spencer forms is bounded by this quantity, namely by theta ij, which is the coefficient of the Weil-Petersson form and the volume. So this follows just by writing down the kernel of the Green's function and the kernel of the Green's operator and the formula. Anyway, this means that we can add the constant of the Weil-Petersson form pulled back, and then the total space possesses a Kähler form whose restriction to the fibers is Kahler-Einstein. Okay, so here is the argument once again. We compute this thing, and we can see here that this thing here is larger or equal to the Weil-Petersson form. Okay, sorry, I should say that the last line contains a misprint. So it says omega x to the n plus first power larger or equal to f alpha star, pullback of the WP form wedge omega x to the power n. All right. And so this is basically the claim. From this thing, we can see that omega x itself is strictly positive definite. Okay, so thank you very much. This is what I wanted to say. Okay, right. So there is a result of Thomas Geiger and myself, curvature of twisted bundles, and in terms of Weil-Petersson metrics, so the same thing for holomorphic vector bundles. And yeah, I should have included that.